Bismillahirrahmanirrahim. Assalamu alaikum and welcome to this session. In this session, we are going to talk about input modeling. In any simulation, we have certain input random variables that are interacting with the system and driving the simulation forward. In the real system, we have certain arrival patterns and certain events that interact with the system to produce the output. Because we are doing simulation to learn something about the model system, we also need to model the input random variables which are capturing the uncertainty of the interacting events that are actually incident on our system and is interacting with our system. So we can envision this in the form seen on the slide, that in the real system you have typically some random input and that is transformed by the real system into some random output, and on the basis of this transformation we want to learn something about the real system. So in the simulation world, we start with random number generator to produce a uniform random number which has the property of independence and of uniform distribution, and it produces a number between 0 and 1, and these numbers, or this succession of numbers produced by the random number generator, as mentioned, has property of independence and of uniform distribution. But a uniform distribution is not always the way real uncertainty works, because in a uniform distribution everything is equally likely. But when we have a system, we need to appropriately see what is the pattern of the incoming random variable. And typically this is something other than a uniform distribution. So we have another step here which transforms the uniform random numbers to some other distribution that is approximately capturing the input distribution of whatever is interacting with our system. This is shown on the slide. And the combination of these two things actually is called input modeling. And the output of input model is represented as X on the slide, and we have input data. And this is what is fed into the logic of our simulation. And the logic of the simulation is an approximation of the real system, and we try to see how the system interacts with the input random variables to produce the output random variables. So today's session is going to focus on input modeling. In a subsequent session, we are going to talk about how we can observe the output data and form estimates about the actual population that represents the output. Because the output data is also a random variable, it has a distribution. So just by observing a few output data points, we cannot say with certainty about the system. So we need to properly analyze it, and that is the topic of another session which would be titled Output Analysis. So we need to emphasize here that input modeling is very essential to successful network performance evaluation simulation studies. The reason is that even if we do excellent design and analysis of our simulation, if we err in the input modeling, then our results are going to be misleading. So no amount of later work can compensate errors in this stage. So we need to very properly analyze the kind of uncertainty in the input random variables and appropriately model them. So today's session is going to focus on these things. The outline of today's session is that we'll be starting with the topic of creating an input model, in which we discuss how do we collect and represent data. Collecting data is important. We want to collect data that is representative of the input distribution, and then we need to think about how do we represent this collected data in a concise form. Should we be using trace files to drive the simulation, or should we be using some distribution? And what kind of a distribution is it going to be? We need to worry about lots of things. We need to worry about the time dependence between successive random variables in the input model. because this is very important. In many real events or in many real systems, the arrival process is auto-correlated, in the sense that whatever is happening now is going to influence whatever is going to happen next. And this is typical in arrival processes, and therefore, because a lot of our study is going to deal with queuing, it's important that we try to capture the time dependence part of the input model. Also, we have seen in previous sessions that internet traffic or the internet workload is highly variable. And a model that has been proposed in this regard is the heavy tail model. But we need to understand that the heavy tail model belongs to the world of extremistan, which we mentioned before. The world in which you have wild randomness. And therefore, we need to be very careful here and model it appropriately, and thereafter analyze such data appropriately. Secondly, after having defined an input model, we are going to describe how can we test the input model and see if it is really a valid model. So we'd be talking of some heuristic techniques that are based on graphical observation of the data, and we'd also be talking about statistical tests that we can do. And we will emphasize that we need to strike a balance and not depend only on statistical tests, but also use engineering common sense. So the first thing we're going to talk about is creating an input model. We can represent this process as shown on the slide now, that we have to observe the input data. This is very important because we don't want an input model that is divorced from reality. Our input model should be a faithful representation and an approximation of the real input data. It is only a model, and therefore it's an approximation because we want to capture just the core elements of the input data. The input data would also have something which may be classified as noise. If we observe the data for any amount of time, it may or may not be representative of the general characteristics of the input data. So we need to generalize from the input trace or the input data that we've collected, and then simplify to create an input model. So there are two important things here. We need to generalize and also simplify. And that is at the heart of input modeling. Having done that, then we have to generate data from the model that we have created, and this data is then fed into the simulation, and that acts as the driving force of the simulation. So firstly, let's talk about collecting and representing data. Collecting data is a very important endeavor. We have to emphasize that if we err here, or if we make mistakes here, if we collect the wrong data, then we will not be able to recover later. So we need to, first of all, nominate the things which are important for us. And it should be stated that we should be focusing on the input variables when we are collecting data, when we want to create an input model. Because for a novice, a common mistake is that we measure what we can easily measure and then focus on that. But for input models, we need to see what are the random variables that are actually driving the simulation. For a queuing system, we can observe many random variables, many measurements on the system. For example, we can measure the average waiting time in the queue. But this is not really an input parameter. The input parameter to the system in the sense of queuing systems is the arrival rate or the inter-arrival time, and the service rate or the service time. These are the things that are important for modeling the input events. And so we need to collect data on this, and there are various ways of doing that. We can use designed experiments where we are in control of the system and we can change the system in whichever way we want. But that is not always practical, and then you can base your data collection on historical records, on observational data. So here we need to see whatever is efficient and whatever is easily practical. The other thing that I want to highlight is the many data annoyances that we have. There are many things that are annoying about data collection, and those things can quickly discredit any input model. There are 5 things here, and all of them start with D. So you can imagine this to be the 5 deadly Ds. So let's read about them. The first thing is the data may be distorted. So whatever data that you have, it may be poorly communicated, mistranslated, or even recorded wrongly. So this is possible. You are recording, especially if you're depending on humans to record the data, it is possible that due to human deficiencies, we are not able to get a good record. It is also possible that we have dated data, that means very old data, that is not representative of the current system. We may have data that is deleted or censored. This is often a function of our observation instrument. If we have an observation interval, we cannot measure something that is going to happen beyond that observation interval. In the sense of statistics, we would refer to this as censoring of data. So if we have that annoyance in our data, we need to be aware of that so we can properly adjust for it. Also, data is often dependent on each other. In computer networks, the workload is often autocorrelated. It is also of a bursty nature. So if a packet arrives at this moment, it is more likely that a packet would arrive at the next instant. And because of the bursty nature, the activities and the idle periods happen in bursts. And lastly, it is possible that the data that is given to you is deceptive. And this is important to realize because as simulation practitioner, you are not always in control of your data. So if you're doing simulation on behalf of someone, you need to emphasize the need of having good data. Having the data, then we can think of ways of representing the data. We've seen many techniques for this in our earlier sessions. Some things that we've already discussed are techniques of using a histogram, techniques of using a distribution of data to visualize what is the distribution of data, in what range of values are we getting the data. Also, we can chronologically record every event that takes place in a certain time, in a certain observation time. We refer to this as a trace file. And this is a very important method in network performance evaluation studies because using this, we can have a very detailed, valid model of the input. But it has to be emphasized that it may not or it may be representative of the general patterns of the data, because what happens on one day may not be representative of what happens every day. So we need to realize this. And also when we talk of trace files, there are issues of it being inflexible. It cannot be easily changed. So in contrast, we can make use of distributions that are abstractions of reality, but they are more easily moldable and more easily changed. And that is a very desired feature in network performance evaluation studies. In trace-driven workloads, we have a trace file in which you have the history of events that happened during an observation interval. And these are ordered according to time. And because this is real input data, we feed this to our system, and this actually drives the simulation forward. So for example, in a queuing system, we can calculate the next arrival and the service time from observing that what happened in the trace file. Typically, arrival patterns are easily modeled in this fashion, and we have to see what data do we want to keep in our trace file. Some important advantages of trace-driven simulation is we automatically have some credibility because the data that we're using is the exact data that was observed on the real system. But then there are problems. We have credibility in a very narrow sense. What if that particular trace file contains trends that cannot be generalized to the overall pattern of input? So we also have the advantage here that by using trace files, we can make use of the same trace file to test two algorithms on or two systems on. And because the input is not changing for both of the competitors, it is a fair comparison. Disadvantage can be stated here that trace files quickly become of very big sizes and they acquire very big proportions. And therefore, in modern networks where we have gigabit networks and a lot of traffic is exchanged, it is impractical to collect data over a very large interval of time. So we have to balance the need and we have to see what information is it necessary to actually have in the trace file, because having packet level information may be too much and it would create a very large file. It is relatively inflexible in the sense that you have what you have. You cannot really change it by changing certain parameters. And in that sense, a trace file is non-parametric. It is only based on whatever data that you have. On the slide now, you can see some examples of traces that have been shared by various researchers that are working in trace-driven simulations. And they have collected data on HTTP, on TCP, and on various protocols, and on various layers, and at various levels of aggregation. And we can make use of this data. We already have a lot of data available. So the process of data collection then goes out of the picture. If you want to, for example, create a new TCP congestion control protocol, you can make use of the existing TCP trace files, and on the basis of that, compare your proposal to whatever is the current state of the art. So this was about trace-driven simulation. The other alternative is referred to as self-driven simulation, in which we just specify the distribution for various input random variables. And on the basis of that, the simulator has the ability of random variate generation, and it creates data itself, and we don't need to specify and provide a trace file. So you can see that on the slide. You see that the inter-arrival time distribution specifies the general distribution of inter-arrival times. And on the basis of this, we can generate infinite number of samples. And they will all have, the samples would have the same statistical characteristics that are associated with the input random variable. So the motivation of using distribution can be described as we now have the ability of controlled modification because of the fact that we have parameters associated with these input random variables. So another aspect is that now we avoid some noise in the trace file, because a trace file may be too narrow in its scope. It may be capturing something that was only specific to that day. Because when we focus on a statistical distribution, we are trying to generalize from that data. We have the added advantage of generalized distributions that are actually capturing the main aspects of the input data. Also, such distribution-driven simulation is efficient in the sense that now we don't have to have excessive storage for storing the trace files, and now it's just a function we have defined the distribution, and the simulator can create random variates according to that distribution at runtime. So let's move forward and keep on talking about distribution-driven simulation. That will be a focus of discussion for some time now. We'll now be talking about empirical cumulative distribution functions. This is going one step ahead of a trace file. If we have a trace file, we are only limited to the events that happen in the trace file. But what if we want to generalize from that trace file and capture the statistical pattern of that trace file? We can make use of the empirical CDF for this, and we call this model a non-parametric model, because this is in contrast to parametric models that are approximations. In this kind of model, the non-parametric model, we are very closely aligned with the data set that we created this model from. As an example, you can see some observations on the slide now. So if we want to create eCDF for this, the empirical CDF, we can create a staircase-like function, and on the basis of this, we can capture whatever is the empirical pattern in the data. So this is a step function that increases by 1 over n, where n is the total number of observations, at the value of each data point. And we can also smooth it to interpolate between the various values. As an example, you can see piecewise linear empirical CDF, and this then allows values to be generated, value between the extremes of minimum and maximum, according to the distribution of data in the original data set. So this then allows resampling. We can sample from the original trace file, which is just a sample of the reality. And from that one sample, we can create infinite number of samples now that we have defined an empirical CDF. One thing that can be criticized about such a model is that because a trace file is an observation just run for some amount of time, it is not going to capture the rare events. And sometimes those rare events that happen relatively infrequently, they may be very important. Like in the case of heavy tail distribution, very extreme events happen, but they happen relatively infrequently. So a trace file will not be able to capture the entire variation in the input data. And therefore, we can also modify the ECDF by adding additional points specifying what is the minimum possible data that we expect, what is the maximum data that we maximum value of the data that we expect. And in such a manner, we can modify the empirical cumulative distribution function. But it must be emphasized that such a model is closely aligned to the data set. We can also have many theoretical distributions that we can use to model the input data. So for that, we need to consider the whole range of input models. So for that, let me specify 3 very important points. The first important point is, should we be using a stationary model or a non-stationary model? A stationary model is a model which is not a function of time. If you have defined distribution or a model for a system, it is going to be the model of the system tomorrow as well. It is a stationary model. It does not depend on time. If the statistical model of input is time invariant, then stationary model is appropriate. But imagine if your statistical model changes. For example, if you are in a supermarket, then there are certain times in which you have a peak load, and at other times you have idle periods. So clearly this is not a stationary process. The distribution which specifies how many customers are going to be in the supermarket, it changes. Sometimes you expect a very high value with high variation, and possibly at other times you expect a low value with some other variance. So we need to see if our model is invariant to time or if it varies with time. And accordingly, we must use the right kind of model. In internet traffic, we have many trends that manifest themselves over the time period of a day, of a time period of a week. So you have diurnal patterns, the patterns of days and nights, the patterns of weeks. But we can also model internet traffic using a stationary model over the appropriate time scale. It may be a very small time scale, but if the statistical model captures the distribution over all time in that range, then it can be used. And it is often used for small intervals of time. But over the time scale of days and weeks, internet traffic is certainly not stationary. We can also use knowledge about, is the input data stream dependent or not? In network traffic, the workload is often autocorrelated. It is dependent on each other. And successive values are more likely to be of a similar nature. So we call this positive autocorrelation. But in many models, we ignore this dependence between successive random variables of a time series. We imagine that we have an IID process. This may or may not be an accurate representation of reality. So we must look at this assumption very carefully. The third thing that is very important is representing the tail behavior. In network performance evaluation studies especially, you have huge variability. And because of that, if you only observe data for some limited amount of time, it is bound to happen that you would miss some extreme event. But that extreme event must be modeled because that extreme event has implications for the network performance. And therefore, modeling the tail behavior is very important. So the input model then must not only focus on the marginal distribution of all the random variables, but also the interdependence between these random variables. We start with the simplest possible thing done by simulators, people who are working with simulation tools, and something that is very wrong, and that is using a mean instead of a distribution. So you want to model arrival process. You know the arrival process has a stochastic nature, but you say, okay, I just know the average. Let's just replace the distribution by the average value. This is very wrong, and this is called the flaw of averages. And in fact, people have written a book on this title. The key idea here is that whenever you have randomness, you must represent the range of randomness through a shape. Example of that shape is the distribution of data. That actually captures the source of randomness and describes what kind of randomness we have. But if we only represent the distribution by an average, then that average can correspond to infinite number of distributions of very different properties. And therefore, it is very dangerous to replace an entire distribution by just an average. And we have seen examples of why this can give very wrong results. In our section on queuing theory, we gave an example in which we were assuming deterministic arrivals and deterministic departures. And we saw that such an assumption, even for the same average value of the arrival rate and of the service rate, gives completely different results to what we would have if we consider stochastic arrivals and stochastic departures. If we only focus on the average, then we are going to be very optimistic of network performance. But due to stochastic variation, the performance actually is worse off. And it is necessary that we understand this and we don't replace stochastic behavior by deterministic behavior. In the book Flaw of Averages, Sam Savage, the author of that book, humorously describes this in the sense of this cartoon shown on the slide. He shows a drunk man wandering on the street, and sometimes he goes above the central line and sometimes on the other side. So the average point is the central line. And on the central line he is safe because no car would hit him. But because this is a stochastic process, that person is bound to be dead because he's going to wander off in front of some fast-moving vehicle. In a similar vein, when we only focus on the central values, it is possible that we are going to be hit by this lurking danger, that we get some very misleading values. So it's important that we take this warning seriously. We should not model a distribution by its mean in a simulation study done for network performance evaluation. So what do we do when we have limited data? So we start from the assumption that we have very little data. So one thing that we can do is that we can go around and ask people who are experts in these areas. And they can often provide us estimates of the minimum value and of the maximum value. And on the basis of that, we often make use of the uniform distribution, sometimes rather inappropriately, because in most cases, it is not equally likely that we get a value that is anywhere between the minimum and maximum value. We often have an estimate of what is going to be the most common value. So if we have that information as well, instead of using the uniform distribution, we can make use of the triangular distribution. So this is a big improvement over uniform distribution because this more closely captures the reality of computer networks and it is more relevant. So we must avoid uniform distribution unless we can not even estimate the most common value. So let's now consider the whole range of input models that we can have. It's important to know this because if we do not know this, we are only going to focus on the case of univariate IID random variables. That is the scenario which we are most familiar with. We only have a single random variable. We describe it using its distribution. And we assume that that distribution is going to hold for all possible instances created by that process. But we've seen that you also have dependence amongst random variables. You have the case of non-stationary models in which the parameters of the model also change with time. So firstly, let's classify input models as being divided into two broad types: time-independent models and stochastic process models. So in time-independent models, we are not seeing how the random variable evolves in time. So in such a case, we can further divide a time-independent model into univariate and multivariate classes. And we are most familiar with univariate time-independent models that are independent and identically distributed. So because this is a time-independent model, if we choose another value, it is going to be independent of whatever we've chosen before, because we are not considering a stochastic process or a time series in which there is some dependence between successive random variables. So we have seen many examples of univariate time-independent input models, and I refer you to our discussion on the various kinds of distributions that we've already covered. Some examples would be binomial distribution, Poisson distribution, exponential distribution. These are all examples of univariate time-independent input models. So a Poisson distribution is a discrete random variable, while an exponential distribution gives us a continuous random variable. Similarly, normal distribution is also referring to continuous random variables. There are certain classes of distributions that are specifically designed to be very flexible, and we're going to talk about them. So one such curve or method of creating a distribution is the Bezier curve, which is very flexible, and we can choose any value, any distribution shape that we desire. And there are other examples as well of very flexible distributions. So there are also multivariate time-independent distribution, in which you have dependence between random variables, but they are associated with each other and they are not dependent on time. It's not the same process, and the random variables are some different, refer to some different times. So when we consider a multivariate time-independent input model, we're actually capturing the dependence between various different input random variables. We can also classify that into discrete and continuous random variables. It's important to highlight here that this is by no means an exhaustive taxonomy of the kinds of distribution that we have. The aim of showing you this classification is just to highlight that we are not limited just to the case of univariate IID random variable models. We have many different models as well. So now we get to the more interesting case where we are talking about stochastic processes. In a stochastic process, you often have a succession of random variables that are indexed by time. And therefore, in many cases, you also have some dependence between these random variables. So we can firstly classify the stochastic process into two kinds. You can think of discrete time stochastic processes. You can also think of continuous time stochastic processes. Furthermore, we can divide the discrete time stochastic process into discrete state stochastic process and continuous state stochastic process. Both of these can be used to model the input random variables. So it's important that we just not focus on the Poisson and the exponential distributions. We can make use of all the models that we've studied in our sessions on stochastic processes. Example of discrete time stochastic process is the general case of Markov chains. And Markov chains can also be stationary or they may be non-stationary. And when we studied Markov chains, we referred to this property by being homogeneous or non-homogeneous. A homogeneous Markov chain, in such a chain, the transition probabilities are not a function of time. So we would call such a chain a stationary Markov chain when we refer to the transition probabilities. And there are also ways of seeing if it is stationary or not. The important point is that in a stationary model, the statistical properties do not change over time. I must emphasize here that there are various kinds of stationarity. You have strict stationarity, and that refers to the joint distribution of all the random variables. If that does not change with time, then we have strict stationarity. That is often a very restrictive case. We also have some relaxations of strict stationarity, and these are the models that we are more interested in. So we would be seeing a model known as covariance stationary model, in which the mean and the variance does not change with time, and also the covariance between random variables is also just dependent on the lag between those random variables. In other words, it is only dependent on how separated they are. It does not depend on what time you're considering this. So in contrast to stationary models, we also have non-stationary models that do not have these properties. What is the need of focusing on stationary models? The need is because whenever we are observing some output, then our life becomes easier in the sense of analysis if we can assume that there is some stationary model that is producing this output. Because if we have a non-stationary process that is creating the output, then everything is a function of time, and things become very complex and messy, and it's very hard to analyze such data. Stationary models, just like IID models, are very simple, and therefore we focus mainly on stationary models because of the ease of their analysis. For continuous time stochastic processes, we can also divide continuous time stochastic process into discrete state and continuous state, and furthermore, they may be classified into stationary and non-stationary. Some examples are relevant here. So I've talked of Markov chain. When we talk of discrete time continuous state stochastic processes, there are many models that are developed in a subject known as time series analysis. A time series is just a stochastic process that is ordered in time. And we have many elaborate theories for this, especially for analysis of financial data. And some models from that subject are shown on the slide. You can see the ARMA model, the autoregressive moving average model, and the ARIMA model. The ARIMA model is used for modeling non-stationary data that has some trend. So we're not going to focus too much on that, but just the intention here is to highlight the diversity of the models that we have. And then you have discrete state, continuous time stochastic processes. We've seen examples of those, a Poisson process, renewal process, which is just a generalization of a Poisson process. We have semi-Markov chains. An important process here is the non-homogeneous Poisson process, in which the rate parameter changes with time. And this is important when we want to model non-stationary data. And lastly, Markov process is a continuous time stochastic process. So let me now move on. We've seen the whole diversity of models. Let's see how can we choose the right model. And for choosing the right model, we can inspect, first of all, the graphical representation of data. We can see the histogram, and from that, we can already know a lot about data. For example, is the data bounded? Do we have a minimum maximum value? Is the distribution approximately symmetric or not? On the basis of this, we can choose certain distributions. And I'm going to come to that very soon, but I will now like to highlight that there are two main kinds of popular distributions. The first main kind refers to those distributions that are easy to work with. We refer to these as mathematically tractable distributions that have mathematical convenience. Distributions like Poisson, exponential, and normal distribution. There are also some other distributions that are very flexible, and they can be parameterized to model any arbitrary data set. But it's important to highlight that for the modeling process, it's important to also gain insight from the physical interpretation of whatever you're trying to model. So there are various guidelines that you can use in this regard. So you have a table shown on the slide now. You can see various distributions. And for example, we know that a binomial distribution results from number of successes in n trials. If we want to model the number of successes in n trials, we must use a binomial distribution. Similarly, we have reasons written out for all the other distribution. A Poisson distribution refers to and models independent events occurring in some time or space. Exponential distribution models the time between two events that are independent. It also refers to process times that are memoryless. And then there are generalizations of exponential distribution. And these are important because whenever we want to model some time in network performance evaluation study, time can never be negative. So it's not really appropriate to model times with a normal distribution because a normal distribution has tails that extend on both sides of zero. So you can also have a negative value return from normal distribution. But for modeling time, we can make use of exponential distribution and generalizations of that. The gamma distribution, the Erlang distribution, the Weibull distribution, and so on. Also, some distributions are important for capturing data that is highly variable. And in this regard, we have the log normal distribution that can be thought of as a product of a number of component processes. We also have the Pareto distribution. So it's important to first of all see what is the thing that we are trying to model, and then on the physical basis of that process, decide on what model that you want to check if it's a good match for it. You can also rule out many models just by checking the physics of whatever you're trying to model. Generally speaking, finding the best distribution is a task in first of all hypothesizing the right distribution and then calculating the values or the parameters of that distribution. You can see on the slide input data histogram is shown, and the same data can be fitted by many different distributions. We see that it can be fitted by a normal distribution, a log normal distribution, triangular distribution, and Weibull distribution. Generally speaking, when we have a distribution that is highly parameterized, we can match the data set very closely. So we then need to revisit our assumptions and see what is the best fit for the purpose of our simulation. Because it's important to realize that all these models are approximations of reality. Real data is not being generated by some distribution. So whatever is important for our modeling, we must cater that into our mind and choose the right approximation. I will highlight a few techniques that we can use for parameter estimation without going into much detail. The name of the techniques are maximum likelihood estimation and the method of moments. And you can find details in any standard statistics textbook. Let me highlight very briefly some advanced models that we must know of and use if appropriate for our simulation study. We can make use of the flexible models I've already alluded to, models like the beta distribution, the Bezier distribution, the Johnson distribution, if our purpose is to very accurately model the data set. These distributions are highly parameterized and they can model the data very closely. Also, we have many non-stationary models, an example of which is non-stationary or non-homogeneous Poisson process. And the rate in such a model changes with time. So it may be appropriate for our simulation and we may consider these models. Let's move on and now talk of evaluating time dependence. We must not ignore time dependence because in computer networks, the system has a lot of memory. In network routers, you have buffers, and these buffers hold packets, and therefore the subsequent service to packets are going to be affected. In that sense, packets coming closer together are going to have similar service, and therefore it is almost a certainty that network traffic workloads would be correlated. So how can we model that? Let me first of all give you a warning, in the sense that it has been proven time and time again that internet traffic is not IID. I refer you to the discussion on fractal traffic and on self-similarity, where we discussed how internet traffic is highly correlated, and even we've seen that the autocorrelation function decays hyperbolically. So you have a lot of correlation, and you also have a lot of variability. And it's important to realize this, because if we do not consider the autocorrelation, our network performance evaluation results are going to be very, very wrong. So we must take this into account. So let's now talk about some advanced models that can capture time dependence. So one model that is used in time series analysis is the autoregressive model. This produces output that can be, by appropriate choice of the parameter, made either positively correlated or negatively correlated. Where positively correlated means values that are close by are alike, and negative correlation is that the random variables that are together in time happen to be negatively dependent on each other. A higher value will be followed by a lower value. And then you also have multivariate models that capture dependence amongst different random variables. It's important to see the difference here. Autocorrelated models model temporal dependence between random variables that are separated in time, but they refer to the same process. For a multivariate model, we are modeling dependence between different inputs. An example for this is the bivariate normal distribution, and there are various other models as well. Lastly, in this part of the section, I want to talk about the tail behavior. As mentioned before, we must not ignore this, and it has been shown again and again that many aspects of network workload is highly variable. So in this regard, when we want to capture highly variable data, it's not clear what kind of a model that we want to use, because it turns out that if we want to capture the body of the distribution, such models typically don't perform very well in the tail of the distribution. And you have other models that are very good for capturing the tail of the distribution, but not the body of the distribution. Also, when we have heavy-tailed workloads, analyzing the output of such systems is very hard, and we will talk about this in output analysis. But I will just say here that we are divided about what is the best distribution for capturing highly variable data. Log normal and bounded Pareto distributions are often proposed as good models in this regard. Now we will briefly discuss that if we have decided on the right input model, then how do we actually test if we have the right input model? So we have both heuristic techniques that are best effort techniques that depend on intuition of the person observing, and we also have statistical techniques. So let's start firstly by heuristic techniques. Generally, heuristic techniques depend on graphical depiction of data and a person observing that and eyeballing the various distributions, mainly the empirical distribution of the data that you have versus the hypothesized distribution. And if you see that, is there a close match between these two? If there is a close match, then you've done your job well of modeling the input. But if there is a big discrepancy, then we need to probably go again and find a new input model. But it is almost a certainty that you will never have an exact match. So what match is good enough and what match requires us to go back? This then question is open to interpretation. Using statistical test, we get an objective answer, but even then we need to realize that any input model is an approximation. And if we consider a very large sample, you would always have differences. So we need to use these techniques, but also use engineering common sense. So in graphical test, mostly we are comparing the cumulative distribution functions. You can see on the slide now that we are comparing the actual empirical CDF with two hypothesized distributions, the exponential distribution and the log normal distribution. So from the graph on top, you can see that there is some discrepancy between the ECDF and the model distributions. This can be more easily visualized by an alternative depiction of the same data in what is known as a probability difference graph. And you can see from this graph clearly that the difference between the ECDF and the exponential distribution is more than the difference for the log normal distribution. And on the basis of this, we can subjectively say that log normal distribution looks to be a better match for our input data. We can also do some other tests, and one very popular method is the use of probability plots known as the PP plots and the QQ plots. In the PP plot, we are graphing the two CDFs directly together. In the x-axis, you have the values of the ECDF, and on the y-axis, you have the values of the model CDF. And for every observation, you see what is the corresponding value on both of these distribution functions. And on the basis of this, you draw a graph. The perfect match would indicate itself in a straight line that is at an angle of 45 degrees. But obviously, because these are not exact matches, you would have some discrepancy. You also have an alternative plot which can be thought of as an inverse of a PP plot. In a PP plot, we are plotting the CDF values. But what values correspond to those CDF values? We can take the inverse of those CDF values to determine the quantiles. And we can draw the quantiles. Similarly, the observed quantile would be on the x-axis. The model expected value would be on the y-axis. A perfect match would show itself in a straight line at 45 degrees. Such a test is better than a PP plot for determining differences at the tail of the distribution, whereas the PP plot is better for checking discrepancies in the middle of the distribution. So these were some heuristic methods. For statistical methods, I refer you firstly to the discussion on the chi-squared method that we've done previously, and I would supplement that with a new method known as the Kolmogorov-Smirnov test of goodness of fit. This is just a formalized version of the test we saw earlier, in which we were comparing two CDFs. Now we plot the CDFs again, but now we are going to see the maximum distance between the two CDFs. And then we determine if this difference is large enough. We determine this by looking up a table based on the degrees of freedom of our data and seeing if our value is larger than some critical value. And on the basis of that, we can either reject the null hypothesis or fail to reject the null hypothesis. So this was a statistical test that we can use for checking the goodness of fit. Let me now conclude this session. I will conclude this session by relating to you 7 habits of highly successful input modelers. This is from an article by Larry Lemus, the author of a book on discrete event simulation. So he says that the 7 habits are, first of all, collecting the right data. Secondly, using the full range of input models. Thirdly, performing a complete statistical analysis. Fourthly, evaluating time dependence. Fifthly, considering both parametric models and non-parametric models. And the last 2 points refer to doing a proper sensitivity analysis and considering the tail behavior. The need of sensitivity analysis is to focus then on input models that have a substantial effect on the output. If you have an input random variable which is having a big impact, then it serves us to do a more detailed study and create a more detailed and a more accurate model. So this wraps up the lecture today. I will see you next time, inshallah. Assalamu alaikum.